Welcome, ladies and gentlemen, to this video lecture. Let's take a look at this example. So we are given a function defined as follows, defined as this integral, and the question is sketch the graph of f indicating its turning points, its y-intercept, and its behavior at plus and minus infinity. So all we want to do is we want to sketch the graph of this function big F. Okay. Let's start with the y-intercept. So y-intercept when the x coordinate is 0. So f is defined as the integral from 0 to 0 of whatever, but we are our bounds are the same, so that is actually equal to 0. So in fact our function goes through the origin. Okay, so this is our y-intercept. Let us think about our turning points. Okay, so where do our turning points happen? That is where the derivative of big F is equal to 0. So firstly, by the fundamental theorem of calculus, we can work out what the derivative of big F is. And what is the derivative of big F? That is x cubed minus 3x squared plus 2x over x squared plus 1. And notice here we're never dividing by 0, so this expression or this rational function is continuous. So let's add here, since the function that sends x to x cubed minus 3x squared plus 2x over x squared plus 1 is continuous. And why is it continuous? We're never dividing by 0. So x squared is greater or equal to 0, and then we're adding the 1, so that the denominator is never 0. So here we've got our derivative of big F, and now we solve for x when the derivative is 0. So when f prime of x is equal to 0. Okay, and the solutions of that is x is equal to 0, x is equal to 1, and x is equal to 2. So we've got our intercept here, our y-intercept at the origin. We have a turning point there as well, or a critical point there as well, and at 1 and at 2. And so 0, 1, 2. And we see here on the interval 0 to 1, our derivative is going to be positive. So how do we see that? We take our derivative, once we have factorized it, x minus 2 over x squared plus 1. This part is always positive, the denominator. If we take, for example, the value of a half here and plug it in here, this is so that is a half, that is minus a half, that is minus something. So the something positive multiplied by something positive, and here we've got two negative things, the two minuses cancel out, so the derivative here is positive. So our function goes like that. And we now do similar analysis for all the other intervals between our critical points at 0, 1, and 2, then we see that f prime here is negative. Over here f prime is also negative, and over there f prime is positive. And you do that, you just substitute in values in between your critical points. Okay, so that tells us where our function is increasing or decreasing. Okay, so now we want to be able to describe the function's behavior at plus infinity and at minus infinity, and this is important. We need to think a bit about this. So this is important. The function could either have a horizontal asymptote, or it could go to infinity. So we have to decide which of these is actually the case. Okay, so let us think about the behavior at, let's start with plus infinity. Let us think about the derivative of big F as x tends to plus infinity. So let's think about the limit as x tends to plus infinity of big F, the derivative of big F. But that is the limit as x tends to plus infinity of x cubed minus 3x squared plus 2x over x squared plus 1. Okay, but if you squint a little bit, I will leave this as an exercise. We see here the derivative of big F goes to plus infinity. And I will make a video explaining the following after we have finished this example. So I'm going to make the claim if the derivative of big F, the limit as x goes to infinity of the derivative of f is plus infinity, then the limit of f itself as x goes to plus infinity of f itself is also equal to plus infinity. So I will not discuss this now, but I will include a video discussing why this is true. Okay, so now we see that the derivative, so here we have seen that the derivative goes to plus infinity, and since the derivative goes to plus infinity, the function value of f itself goes to plus infinity, so the function actually goes to plus infinity. So that is the behavior at plus infinity. Let's think about the behavior at minus infinity. So again, let's think about the limit, but now as x goes to minus infinity of the derivative of big F. So that is the limit as x goes to minus infinity of, what is it, x cubed minus 3x squared plus 2x, x squared plus 1. And if you squint a little bit, you will see that this goes to minus infinity. And now, same as before, what do we have? I will make the claim that if the limit as x tends to minus infinity of the derivative of f of x is equal to minus infinity, then the limit as x tends to infinity of f of x is equal to plus infinity. So here is something different. So you can think of why this should happen. So if we think about what is going on, so over here our derivative is negative, but if we move further negative, it becomes more and more negative. So our function actually, the function values actually goes to plus infinity. So I will not discuss this claim now, but there will be a video discussing this claim afterwards. Okay, now we have the behavior at minus infinity, plus infinity, and we have our turning points and our y-intercept. So let's sketch our graph. So our function has a turning point at 0, 1, and 2. Function goes to plus infinity, and its derivative gets steeper and steeper negative. It has a turning point there, has a turning point there, has a turning point there, and it goes to plus infinity as x goes to infinity. So here is a rough sketch of our function, or the graph of our function. So just for interest's sake, maybe we should write out the definition of the graph of a function. So the graph of f. So the graph of f, that is a set of points in the plane R2, is defined as, so we use set builder notation, x, y, all the points x, y, so that in R2, so that y is equal to, satisfying the condition that the y coordinate is equal to the function value of the function at the given x coordinate. So when you see the graph of a function, that is a set, and it is that set. Okay, that is it for this example. I will see you in the next one.